Alright, so we're continuing our discussion of data clustering, and I just wanted to talk about a general definition before we get started, some math notation that you may or may not be familiar with, and that is the indicator function. Sometimes called the characteristic function. Sometimes denoted by one with a set, some kind of set notation underneath of it, and another way to talk about it is with chi with a set notation under it. So in LaTeX, that's a chi. Oop, there we go. My hand keeps hitting the pause button. Sorry about that. Uh, so yeah, this symbol right here is the LaTeX chi. Or I should say Greek. Okay, and so what does this do? Oh, this is set notation, not a. So what does this do? One, like one sub a is equal to 0 if the x that you're looking at, if the point is not an element of a, and 1 if the point that you're looking at is an element of a. So typically you would see something like 1a of x, right? I like to put that as a function notation. Some people don't. That's in our notes. We're using the chi, and so chi sub I in our case is going to indicate which cluster we're in. And so R chi I is going to be 0 if the x that we're talking about is in cluster I, not in cluster I, or 1 if x is in cluster I. And so we need to use some function argument there. So chi I of x, I should say, is equal to 0 or 1. Okay? And so we use that because it makes the the notation a lot easier when we're talking about like the error function for cluster I is going to be defined to be actually this is distortion error. Distortion error is going to be defined to be the average 1 over the number of points in cluster I, number of points in cluster I, times the sum from I, let's say from k equals 1 to n, let's see, I guess we have n sub I points, right, in there. And then we'll take the distance between x, k, oh actually this is the number of points in our data set, minus c I. I'm using different notation in the notes. Sorry about that. And let's get this written down here so we can take a look at what this is. Okay, so if xk is in cluster I, right, this quantity is the distance squared, right, to the cluster center. Otherwise, this quantity is 0. And so this quantity then is going to be 0 exactly n sub I times, right? 1 for each element of the cluster. Good. All right. So then the overall distortion, this is the distortion error on cluster I. And so then the overall distortion error is going to be, the sum of the clusters. 1, 2, How many clusters do we have? P, E sub k. Good. All right. So what does that mean geometrically, right? You might have a C here and then some X's out here. Okay, so the distortion error on this cluster would be these distances squared, the sum of all of them. Actually, it's the average of the squared distance between the data and the center, right? And this would be the distortion error, or one way of looking at the distortion error on cluster I. Good. And so that's one way to get kind of a feel for how the data is spread out in your clusters. So if you have a very low distortion error, that means the data points are tightly packed around your cluster. And then if you have a large distortion error, that means you might have some data way far away from the cluster center. Good. So it may or may not be good. Did you see my air quotes there, or hear my air quotes? Okay. So that's the distortion error is a common measure for how good a clustering might be. But some data points or some sets you may not want to use the distortion error as a measure of goodness. This is just one way of doing it. Okay. So our first method is the workhorse of the clustering world, and that is K-means clustering. And so there's some talk about I talk about the name of the clustering a little bit in the notes, but we'll just keep it short for now. Our clustering method here is going to be the following. Actually, this is a pretty easy technique. We'll just write it down. So input to the algorithm will be the data points, and K will be the number of clusters desired. Okay, and so again, output will be the membership function, okay, and to tell you the truth, the membership function for this is pretty straightforward. It's the one that we used for the Voronoi cell. So the membership function M in the case of K-means is going to be I if, you could put an if and only if you want. I did in the notes for some reason. If the distance between X and Ci is less than or equal to the distance between X and Cj for all I not equal to j, and of course then j is running from 1 to p. So you're testing all the cluster. Whoops, all j is going from 1 to k. Sorry about that. I see an error in the notes then, because we're testing it against all the cluster centers, right? And so if you have cluster centers here, here, and here, and here's my x value, right, it's pretty clear that the distance between x and this first cluster is going to be less than any of these others. And so I would say that x belongs to, if this is C1, cluster 1. Cluster 1. Good. And so this is going to be the membership function that we're going to use. And so typically we don't have to define that, although it is possible, right, to go in and actually define what the magnitude is, what the distance function is. We're always going to assume that we have the Euclidean distance, but that's not, you could change that pretty easily if you wanted to. Okay, so the algorithm itself continues then. So to initialize, select k points at random. Okay, so there's a question here. How do I do that? The reason I ask is because should you use data points to represent the centers, or should you just put k centers just randomly in the plane? And I would say you should put k points of the data as your initial centers. So use k points of data as the original centers. Okay, those are the CIs. Good. Then what do? So now we will repeat the following. We will sort the data according to our membership function. And then we reset the centers. Reset the centers as the centroid of each cluster. That's it. You repeat over and over again. Of course, we have to have some kind of stopping criterion. So kind of a typical stopping criterion might be that you'll have like a maximum number of iterations you want the algorithm to go through, or you might have a minimum number of, or minimum distance that you want the centers to change. So if the centers aren't changing anymore when you reset the centroids, then you could stop. Okay, so in the next example, we'll go through a numerical example of the KMeans algorithm. See you then.